Okay, now if you've had calculus, you can verify what I'm about to tell you. And if you haven't had calculus, you can still see how the calculus works. And the calculus of this, calculating what we call the derivative and an antiderivative, are actually fairly simple calculations once you know the rules. You don't know the rules, then it's kind of mysterious, and we can leave it as mysterious for now. But when you take calculus, you're going to get some simple rules. You can come back and look at this and find out exactly how these expressions were obtained. In any case, our function is y equals 3 plus x squared. Its derivative, and I'm not going to explain that, I'm just going to assert it. If you know calculus, you can tell very quickly the derivative is 2x. Again, once you know the rules, that's easy. An antiderivative would be x cubed over 3 plus 3x. Right there it is. And those are really easy. If you have that question on a calculus final, you'd be very joyful. That would be a very easy question to answer. Okay, well, whether you know what these things are or not, well, I'm going to explain what they are. Okay, well, we evaluate these. We have x values from 0 to 2. We evaluate 2x. It's very simple. We just double all these. Instead of 0.5, 1, etc., we get 0, 1, 2, etc. Now, evaluating x cubed over 3, that's plus 3x. That's fairly easy to do when x equals 1. X cubed over 3 is 1/3. 3 times x is 3. That's 3 1/3. That gives us 3.3 repeating. Now, and for 2, it's also fairly simple. 2 cubed is 8. 8/3 is 2 2/3. And you add that to 6, you get 8 2/3. Okay? These others, 0.5 and 1.5, well, cubing those numbers takes a little bit more work, and it's not as obvious. But this is obtained. These values here are obtained by simply plugging these numbers into this expression. And I'll point out that I used y with an apostrophe. That's read y prime. So y prime here is our 2x evaluated here. And this is like a big fancy y, okay, to distinguish it from just your regular y. And those values are, as we say, you can plug these numbers in, the x numbers in, and you're going to get these. Okay, now, two things I'm going to do. Okay, the first interval, y prime is going to go from 0 to 1. It's going to average what? Well, it's going to average 0.5. On the second interval, y prime goes from 1 to 2, and it averages 1.5. On the third interval, we go from 3 to 4, and averages 2.5. Those are identical to our slopes, and our slopes are the average slopes over each of these intervals. It turns out that the y prime does give us our slope, so that when we average the two slopes on the interval, we get the average slope in this case, and it's exactly the case for this function. Now, that only works if your function is a quadratic function. If it's not a quadratic function, if your interval is small enough, these numbers would be close to these numbers, but they wouldn't be expected to be exact, as they will for a quadratic function. And if you've had calculus, you might want to stop and think about why you get exact approximations if the function is quadratic. Okay, the capital Y, that's called an antiderivative function. This is a derivative, this is an antiderivative. You got y sitting here, you got its derivative here, derivative gives you slopes. Antiderivative is related to areas in a very simple way. The antiderivative at 0, for the antiderivative I chose. Now, there's an infinite number of possible antiderivatives, and I don't want to get into that, but at least for this antiderivative, its values, well, are these. And the accumulated areas, as you can easily verify, are these. And these values of the antiderivative correspond very closely to the values of the accumulated area. There's only a 1 or 2% discrepancy between these numbers and these numbers. The discrepancies are all between 1 and 2%, except for, of course, 0, which is the same both times. So you have this close relationship, so that this graph is confirming something we know from calculus. Once we know calculus, we know that the change in the antiderivative between here and here, or between here and any point, has to equal the accumulated area. Okay? the change in the antiderivative from here to here is equal to the accumulated area under the actual graph. Now, why are these different? It's because the actual graph is a curve, and this is an imperfect approximation of the curve by straight lines. You might recall I commented earlier, it looks like between a 1 and a 2% error, and I did that by visualizing. I hadn't calculated it. That was a little surprised. It came out just as I said. It was just dumb luck, but I knew it was a pretty small difference. Okay, there's a small difference due to the fact that you have straight line approximations, broken line approximation, instead of a smooth curve. The smooth curve goes underneath the broken lines so that these values are all smaller than these values. Now, if you've already had calculus and don't completely understand that, you want to go back and really think about all the relationships. But all I'm saying here is that the y prime is your slope. The big fancy y is your accumulated area, or at least your antiderivative, and the accumulated area is the change in the antiderivative. And if you don't know that, if you haven't had calculus, well, it's worth keeping in mind. There's this thing called a derivative that's easy to calculate for this function, harder for some. Antiderivative that's, again, easy to calculate for this function if you know the rules. And these numbers here are approximations of these numbers. Now, here's a really big idea. The interpretation of the derivative is the same as the interpretation of the slope, and there's a very clear connection between the derivative and the slope. If you've had calculus, you should completely understand what that connection is. If you haven't, you should understand that interpreting these slopes is the key to interpreting what calculus tells you about real-world models. And the interpretation of the antiderivative. Now, I put a caret in here because I decided there needed to be the adjective change in here. Interpretation of the change in the antiderivative is the same as the interpretation of the change in area. So change in area on a trapezoidal graph, change in the value of the antiderivative, they mean the same thing. Once more, if you've had calculus, that's something you should really understand and work to understand, because most people come out of calculus without the ability to immediately understand that. It's the key to using mathematics and engineering in any field where you're using calculus, where you're trying to model a system or a situation. And if not, take into mind that's the reason we're developing this trapezoidal approximation graph, because you have calculus that makes all this exact and makes it easy to compute and extremely powerful. So learn what you can about trapezoidal graphs and transfer it over to calculus when you learn it. If you've learned calculus and don't understand how this connects, work to connect it.